I stated in an earlier video that while some of the rules that you've learned for real numbers will also hold for matrix arithmetic, others don't. And I cannot stress enough how it is important that you assimilate those facts, right? You need to learn what things you already know still hold, and what things you knew about real numbers will not carry forward into your work you do with matrices. So let's start with some examples. In fact, that's all we're going to do is work some examples. If we were talking about real numbers, okay, then if I had that a times b was equal to 0, then that would mean that a was 0 or b was 0 or both, right? We also know that if a and b were just real numbers, then a times b would equal ba. And finally, if a and b and c were real numbers, and there's going to be a trick here, we'll come back to that. But if a and b equaled ac and these were real numbers, then we would cancel out the a's and conclude that b was equal to c, right? Like I said, there's actually a caveat to that, right? Let's use this a, b, and c and see if these things hold, right? So first let's do a times b. Clearly we can see these aren't equal to 0, but is the product equal to 0? So I have 2 minus 2, 0. 4 minus 4, 0. 2 minus 2 is 0. And finally 4 minus 4 is 0. So this is an example of what we call a zero matrix. Okay, it's just a matrix of all zeros. So yes, it was true that AB was equal to 0, but clearly we didn't get there by having any zeros. There's not a single 0 here. Okay, so we can't look at this and make those kind of conclusions. What about AB equals BA? This is AB. BA is equal to this. So here I have 2 plus 4 is 6. That's already different because these are all zeros. Then I have minus 1 plus minus 2 is minus 3. Here I have 4 and 8 is 12. And then minus 2 plus minus 4 is minus 6. So clearly AB is not equal to BA. And then finally, let's do AC. So 2 times 5 is 10. Minus 10 is 0. 2 times 10 is 20. Minus 20 is 0. 2 times 5 is 10. Minus 10 is 0 again. 2 times 10 is 20. Minus 20 is 0. So we do have here that AB is equal to AC. But what about B equals C? Are they the same? Well, no, they're not the same. Now, it turns out this actually is the same rule as it would be for real numbers. If you think about it, you're used to doing something like this probably. I am too. If I had real numbers A, B, and C, and say if I'm just doing algebra, right, we would do this, right? That's why I put the star here. But is that always true? Well, no. And let's think about what's actually happening here. There really is no formal mathematical rule that says I can do this. The actual rules come from the axioms for real numbers, and there's two at play here. One of them says that if A is a real number, and I multiply it by 0, or excuse me, by 1, then I just get A. The other one says that if I have a real number A, and multiply it by its multiplicative inverse, 1 over A typically, that's equal to 1. But this does not apply if A is equal to 0. Okay, so if I'd had this, 0 times 3 is equal to 0 times 7, it's true that 0 is equal to 0, but if I cancel out the zeros, I get 3 equals 7, which obviously isn't true. Okay, so whenever you're canceling out, you're really doing these two steps. You're multiplying by the multiplicative inverse, right? That then gives you a 1 right here. So you have 1b equals 1c And then we know 1b equals b, 1c equals c. And then we conclude b is equal to c. But it doesn't work when we have 0 because 0 doesn't have an inverse. So what about this right here in this particular case? Well, it turns out that square matrices can have inverses as well. All right, we're not ready to talk about how to find them, but it's possible for a square matrix A to have an inverse. And unlike, because we don't have division matrices, unlike with real numbers where you just divide 1 by the real number, you're not going to find the inverse of A by doing this. Right? Like I said in another video, we'll see how to find the inverse. But if A has an inverse, they have A times A to the minus 1 is equal to A to the minus 1, its inverse, times A, which is equal to an identity matrix. Well, that's like this rule, right? And then we know that an identity matrix times some matrix is just equal to the original matrix. Well, that's like this rule. Okay? So if we're really applying the same rules to go from AB equals AC down to BC, like I said, why is B not equal to C? For the same reason these two aren't really the same. 3 is not equal to 7. This particular A does not have an inverse. Therefore, I can't do this. If A had an inverse, then I could do this. This becomes identity matrix times B, identity matrix times C. I could do all that. But this A does not have an inverse, so I can't do any of this. That's the reason why, even though AB was 0 and AC was 0, we cannot conclude that B is equal to C for the same reason that 0 times 3 is 0 and 0 times 7 is 0, but 3 does not equal 7. But we'll see how to find inverses later. We have to learn a few more things along the way. Okay? But hopefully, examples like this are helping you start to understand that what you think you already know about real numbers does not necessarily apply when we're dealing with matrix arithmetic.